Let's say you need to send a highly sensitive file to your coworker, a database password maybe. You don't want anyone on the network to see it, so you just lock it in a digital vault. You send the vault over the internet. Your coworker receives it, it pulls out their key, unlock the vault, and read the password. Simple flow, right? That simple idea, locking and unlocking a vault with the exact same key, is the foundation of symmetric encryption, and it is the oldest trick in the book. But as you are about to see, while this is the fastest way to protect your data, it has one massive fatal flaw that almost broke the internet. In symmetric encryption, the rule is absolute. One key rules them all. So if you have the key, you have full control. If you don't, the data is just mathematical garbage. Because it only uses one key, symmetric encryption is incredibly fast. That makes it absolute workhorse for digital world. So when you lock your iPhone, what is the answer? Symmetric encryption. When your company encrypts its massive cloud databases, it's always symmetric encryption. Your hard drive, your password manager, your encrypted backups, they all use it. So whenever a computer needs to scramble gigabytes of data in milliseconds, symmetric encryption is the only tool for the job. Today, almost the entire world uses one specific symmetric algorithm, that is AES, Advanced Encryption Standard. But here's something that confuses a lot of beginners. AES is not a secret. The exact math, the code, the blueprint of how AES works is completely public. Anyone can download it. Hackers knows exactly how the lock built. But security doesn't come from the hiding the algorithm. Security comes from hiding the key. AES acts like a massive mathematical blender. It takes your data, chops it into fixed size blocks, usually 128 bits, and runs it through multiple rounds of insane and intense scrambling using your secret key. Because it encrypts data in chunks, we call it AES, a block cipher. But now we run into a very dangerous problem. Let's say I take the word hello and I encrypt it with a secret key. I get the block of ciphertext. But if I encrypt the hello again with the same exact key, I get the same exact ciphertext also. But why is that bad? Because computers are pattern recognition machine. Let me show you. If we take an image of Linux Penguin and we encrypt it block by block using the basic AES, but it looks like this. You can still see the penguin. These colors are scrambled, but because every block of white background encrypted into exact same patterns, the outline is perfectly preserved. So the data is encrypted, but the shape of the data is exposed. So what is the solution for this problem? So to fix this, cryptographers add chaos. Before we encrypt the first block, we inject a random string of numbers called initialization vector or a nonce, means a number used once. Now the math looks like this. We take hello first, we take the secret key, and we take one random initialization vector. So we get the ciphertext 1. Then we take the hello again and the same secret key is there. But we have this time different initialization vector. Because of that, we will get a different ciphertext. So even if you send the exact same file twice, the output looks completely and totally different. The penguin is gone. The patterns are destroyed. We destroyed the patterns. But hackers had one more trick. What if they intercepted your encrypted message in transit? Because they absolutely can do. And just randomly flips bit of that ciphertext that you are sending. So they cannot read it, but they can corrupt it to mess with your system. And this is why today you don't just use basic AES encryption. You use specific mode called AES GCM. So GCM does two things at once. It encrypts the data and it mathematically calculates an authentication tag. Think of this tag like a wax seal on an envelope. When your coworker receives the vault, the algorithm checks the wax seal first. If a hacker altered even single zero or even single one while it was crossing the internet, the seal breaks and AES GCM rejects the entire file. So AES GCM is fast. It hides pattern, it is tamper proof, but I told you at the very beginning there was a fatal flaw. Symmetric encryption requires both people to have the same exact key. But if you and your coworker are living in different countries, how do you safely send them the key? You cannot email it, you cannot even text it. If a hacker is watching the network and intercept the key, all the AES encryption and world class math behind it is useless. They have the key, they win. So this is the key distribution problem. To solve it, the world had to invent a completely new type of math, a system that doesn't use one key, but two. And that is mind-bending world of asymmetric encryption, which we are going to decode in the next video right here. So till then, stay secure and I'll see you there. And remember, we will keep it simple.